Good morning and good afternoon, ladies and gentlemen. Thank you for joining today's webinar for the mining applications. Let me first show you what we have prepared for you today. I will start with a short overview and introduction of the new ARL X900 spectrometer, focusing on its new features. Then we will dive into the applications in mining, focusing on the sample preparation methods and analysis of different minerals. At the end, I will give you a short summary and we will continue to the Q&A session. In March and April, we have finished the webinar focusing on applications of the ARL X900 spectrometer in steel and cement. If you have missed the first two webinars, please feel free to click the on-demand videos. Today, we will focus on applications in mining. The next webinar will be focused on applications in aluminum. The ARL X900 spectrometer is the latest addition to our X-ray fluorescence spectrometer portfolio. With the launch of the new ARL X900 spectrometer, we are reaffirming our commitment to delivering fast and precise elemental analysis tailored to industrial applications. The ARL X900 spectrometer offers both simultaneous and sequential wavelength dispersive X-ray analysis, which can be complemented with an integrated X-ray diffraction system as well. We have equipped the ARL X900 spectrometer with a dual sample loader, large sample magazines, and the capability to integrate it into an automated lab, ensuring the highest throughput and productivity for demanding applications. And of course, the ARL X900 spectrometer comes with dedicated calibration methods and standardless analysis, covering a wide range of materials types. Now let us have an insight into some of the key features and their benefits to your daily work. Our 5th generation X-ray tube with low vac technology is positioned above the sample in a vacuum chamber, ensuring high uptime and protection from debris. This is especially critical for press pellet samples. This design delivers high X-ray intensity for faster measurements and lower detection limits. For flexible and reliable analysis, the ARL X900 spectrometer is equipped with a gear-free goniometer, ensuring long-term precision and reproducibility. The goniometer allows for sequential WDXRF analysis for up to 84 elements without mechanical wear. This elemental range covers elements from fluorine to uranium. The typical elements required in the mining applications are covered. In addition, our design ensures an extremely low consumption of P10 gas, which is essential for remote applications. The dual sample loader is designed for preloading the next sample while the first sample is still being measured, ensuring high throughput without losing time for sample pumping. To maximize speed and efficiency, the spectrometer includes fixed-channel monochromators that enables simultaneous analysis of up to 32 elements, providing rapid and accurate results without the need of moving parts. The SAX detectors offer high count rate linearity, improving precision for crucial matrix elements. Additionally, the integrated XRD system allows for specific phase and mineral analysis, combining two critical technologies in one instrument for deeper insights into material composition and structure. Each ARL X900 spectrometer is tailored to align with the analysis needs arising from your processes, delivering high sensitivity, accuracy, efficiency, and reliability. Here is one example configuration for the simultaneous WDXRF analysis, covering typical elements needed in the mining application. The simultaneous WDXRF uses fixed crystal and detector combinations dedicated to each element. Here the speed is the key. In this example, we can measure each 9 elements within 40 seconds. Such a configuration ensures fast analysis for the highest throughput. I'd like to point out that here all the detectors are sealed, which means there's no gas consumption. Depending on the configuration, the ARL X900 spectrometer can be configured with up to 32 fixed channels, thus analyzing 32 elements simultaneously. In addition to the simultaneous configuration, it is also possible to combine the goniometer with the fixed channels to enable the sequential analysis. The sequential XRF employs a goniometer to capture signals from different elements one after the other. With our GLIS technology, the movement from one element to the next is very fast, around only 1.5 seconds. In this example, we have 6 elements associated with the goniometer and 8 elements associated with the fixed channels. For a combined goniometer and fixed channel configuration, we recommend using fixed channels to analyze trace elements for the optimal sensitivity. In this example, you can increase the counting time to 56 seconds for a single element in the fixed channel configuration. In addition, we selected goniometer in this configuration to analyze sodium. This is because our goniometer is capable to measure sodium in the sequential XRF method. With both sequential and simultaneous technologies, we could optimize the results based on your application requirements. We can also configure 2 goniometers in one ARL X900 spectrometer for the best flexibility and higher throughput as compared to having only one goniometer or only fixed channels. We recommend distributing the elements between 2 goniometers based on the crystals needed. For example, if the goniometers are identical, we would use all the elements with the same crystal on the first goniometer and the other crystals for the second goniometer. Even with 2 goniometers configuration, there is still room for a few fixed channels, which expands your analytical potential. Now let me walk you through the benefits of the newest dual loading system in the ARL X900 spectrometer. With the dual sample loader, we can load the second sample while the first sample is still being analyzed, thus reducing the total time to results for batch analysis. In this example, we compare the numbers of samples analyzed within 1 hour between the ARL 9900 spectrometer and the ARL X900 spectrometer. In this example, we would consider 1 minute counting time with 12 fixed channels and 1 goniometer for analysis of 3 elements with 20 seconds acquisition time for each. With the dual sample loader, it is possible to measure up to 47 samples within 1 hour, as you can see here, whereas with the single sample loader, it is only possible to measure up to 38 samples. Thus, here the throughput is increased by almost 25% with the new ARL X900 spectrometer as compared to its predecessor. The ARL X900 is designed for unattended use. We are able to offer automation solutions either through the robotic arm by the SMS automation family or through the XY sample changer as shown on the right-hand side. The automated labs or workflow improve the accuracy of measurement and analysis precision. It also increases sample transfer speed between different parts of the workflow, for example, from sample preparation to XRF analysis. Now let us discuss what challenges the mining industry is facing when it comes to elemental analysis. The mines are often located in remote areas where the weather condition is harsh. Some mines are even located at high altitude area. In the high altitude area, the lower air pressure increases the risk of arcing in high voltage equipment, which requires really special configurations to ensure reliable long-term usage of instruments, especially for XRF. The remote locations have also limited resources that make logistics, storage, and recycling difficult. It is thus challenging to store and recycle chemical reagents. Such restrictions could make the sample preparation even challenging with atomic absorption or ICP. And due to the high variety of elements in the ores, achieving precise analysis can be very challenging because there is not easy access to certified standards with known percentage values. Last but not least, in some large mines, the high throughput is really required. Okay, now we will show you how we can solve these challenges in the mining industry with our new ARL X900 spectrometer and other products in our XRF portfolio. To provide deeper insight into the applications, I'm very happy to hand it over to my co-presenter, Didier Bonway. Didier, over to you.
Thank you, Ling. Good morning, good afternoon, ladies and gentlemen. Yes, let's go through typical applications in mining industry with X-ray fluorescence spectrometry. First of all, I'd like to talk about the different sample preparation that are used for XRF analysis. The first one would be press pellet sample preparation, because it would provide the best performance for minor and trace elements. When we talk about trace elements, it's less than 0.1% or less than 1000 ppm, or also for the analysis of similar materials. So the preparation is done first by crushing, grinding, and then mixing with a binder if necessary. Second step is to press the sample in a die. Usually 20-ton pressure is sufficient. And finally, we get a nice pellet with a flat surface that is easy to present to the XRF spectrometer. So it's very simple technique to prepare the sample, and that's one of the advantages. So this straightforward sample preparation with grinding and pressing steps. It can be also adapted to small quantities if we don't have enough material. There is no or minimal sample dilution. Maybe the dilution is brought by the binder, but generally we will never use more than 10% binder. In the cases the powder does not agglomerate well, which means we get the highest signal intensities on the trace and the minor elements. The drawback is that the calibration generally can only be done for one type of sample species, like for example, one calibration for cement, one calibration for slags, another one for limestone. But sometimes we can mix together more different minerals and make a calibration, for example, for soils and sediments or for rocks. In these cases, we can cover quite a number of elements, as mentioned here, up to 35 elements in some cases. The second step, or the second way of preparation, is the fused bead sample preparation. In this case, we are going to turn our mineral sample into a glass disc through fusion. In a fusion machine, we see here typical gas fusion machines, but there are also existing electrical fusion machines that are more and more used right now. And by doing this transformation from a mineral into glass, we are going to get some advantages in terms of homogeneity of the matrix, in terms of no problems with the grain size, so no grain size effects. This techniques also removes any mineralogical effects, and in the end it improves the accuracy of analysis, mostly for the majors and minor elements. So typically when we are above 10%, the effect is really quite big. And less so when we are below 10%, from 1 to 10%. One of the disadvantages, of course, is that we are going to dilute the sample. Typical ratio is one part sample and 11 part flux. The flux being a mixture of lithium tetraborate and lithium metaborate, typically. And this dilution means that the limits of detection for trace elements will not be as good as we get when we just press the sample as previously presented. So let's compare now typical results we get with both preparation techniques. You see here on the left calibration curve for silica with press pellet, and on the right, same calibration curve for silica but on fuse bead sample preparation. And you get standard error of estimate, SEE, that is improved by a factor more than 3 going to the fuse bead preparation. Here we are talking about concentrations in the samples that vary from around 40% up to 70%. So again, it works best for the high level concentrations, which are required in many cases in mining applications. So the fuse bead preparation does improve the accuracy of analysis, especially for silica and also for lime, for example, calcium oxide, and for alumina. It's particularly improving silica analysis because when grinding silica, sometimes silica is in the form of little crystals of quartz, which are very hard. And then, although we grind them for maybe a long time, couple of minutes, for example, the grains of silica do not break down, and we still have some grain size effects that cause difficulties of aligning the different samples on the calibration curve. As you can see here in X-ray fluorescence, our calibration curve is a straight line. Usually, we would add some matrix corrections in order to improve the accuracy of analysis also. And typically we see on the left the intensities that are obtained from the detector of the spectrometer, and on the x-axis the concentrations. So now in the case of geochemical analysis, we can talk about two different cases. The first one is the geological exploration. Typical geological surveys. These are large campaigns where many samples are collected and sent to a main laboratory that is going to measure, analyze these various samples. And then a panoramic elemental analysis is needed. These samples are totally unknown, and we want to measure up to 35 elements or sometimes more, typically 9 majors, 26 minor and trace elements. And then obviously the sample preparation will be press pellet preparation in order to detect the trace elements at best. Then the second case we can talk about is the control of a mining or a quarry site. In that case, the minerals that need to be measured, analyzed, are mostly known. We know why we are digging in that mine. We know what we're looking for. And then the list of elements is much smaller, from 10 to 18 elements, for example, sometimes a bit more. But what is important here is the throughput. Depending on the site, it can be quite a lot of samples per day. Also, the elemental analysis will be tailored for the mine that we are trying to control. And obviously, the uptime is very important for the spectrometers and all also the preparation machines. Reliability is very important in these cases due to the number of samples and the speed of analysis that we need. The mine needs the answer about the performance, what is the concentrations they are getting, and as well for the finished product that are shipped. So in these cases, either press pellets can be prepared in order to detect the traces at best, or a fuse beads preparation in case the most important is the accuracy on the majors and minors, which is the case, for example, in typical iron ores mining. In both cases, an ARL X900 is suitable. thanks to the fact it is capable of accommodating both full goniometer that will bring the flexibility of analysis and also different fixed channels. And obviously the application with dual goniometer will be very, very interesting for the first case, for the geological exploration, because that will double the throughput of analysis. So let's have a few actual examples here. Nickel ore analysis. We have here an analysis with press pellets. You see here 4 different nickel ores. In this case, we were wishing to get some performance for 8 elements oxides that were known in advance. So they are listed on the right. The goniometer was measuring magnesium, sodium, sulfur, vanadium, and tungsten. You see that the 2 lighter elements, magnesium and sodium, are measured for a longer time, 20 seconds, and only 12 seconds for sulfur, vanadium, and tungsten. The total is 76-second analysis time on the goniometer, which means we can measure on the fixed channels also for 76 seconds. We had 3 fixed channels, nickel, chrome, and iron, and we can measure for the relatively long counting time of 76 seconds on these 3 fixed channels. Here is the typical repeatability that we get on these nickel ores. So after doing calibration curves for all the elements, we run the same pressed sample repeatedly in order to show the actual performance of the spectrometer. We run this press pellet for 25 hours, 1 measurement per hour. We get 25 results. And here you get, on the left, the nickel monochromator data with a nickel content in the sample of 3.7% and our standard deviation over 25 hours of 12 ppm. In the middle, the chrome monochromator data. The sample contains less than 1% chrome, and we get 5 ppm deviation over 25 hours. And on the right, the iron monochromator measuring 18.7% iron. And here we get standard deviation of 49 ppm over 25 hours. So you can see that we get absolutely excellent results in terms of repeatability. And this is the strength of X-ray fluorescence. It's the long-term repeatability of the technique. And also we get quite fast results because each result is obtained in just over 1 minute. We count for 76 seconds. If we add a loading of about 30 seconds, we are going to be in less than 2 minutes. Each result is obtained for this analysis, which means also high sample throughput. And also we can see the quality of the results is excellent. Another example here for iron ores. For iron ores, the important point is to make sure the concentrations of iron is effectively what I'm going to ask the customer to pay for. And of course, the customer is also going to customer who buys the iron ore is also going to check the content of iron in the iron ores in order to be sure he's going to pay the fair price for what he's buying. So there is a reference calibration for iron ores. It is the ISO 9516 method. It covers 22 element oxides. You have here on the table on the right the ranges of concentrations that are covered by this ISO method. And it's a standard method for XRF analysis. It's very well described how to prepare the samples and what kind of reagents and chemicals to use for the calibrations. And then we prepare these iron ore samples as fused beads with 1 part sample, 11 part flux, using a lithium tetraborate, lithium metaborate mixture. And this is able to provide the best accuracy possible for these iron ores ranging from around 52% iron up to 71% iron. Plus all the traces that you can see here and the minors as well. Then when we have within the XRF spectrometer an X-ray diffraction capability like we have in the ARL X900, this gives additional capability. That means we are able to get the information about the various iron phases. We have here on the left Fe3O4, a peak for Fe3O4 that we obtain with our X-ray diffraction system in the spectrometer. We have a peak for Fe2O3, and we find a peak of FeO that sits on the edge of a doublet that includes both Fe3O4 and Fe2O3 peak. So there is the possibility to control the presence of hematite, magnetite, and wüstite in iron ores and also in sinters, thanks to this integrated X-ray diffraction module. Of course, in these cases, the sample preparation needs to be a press pellet because the fusion preparation will remove totally the crystallinity of the sample, and therefore it will not be possible to distinguish between these three iron phases if we prepare the sample as a fuse bead. Another example, using now a benchtop EDXRF spectrometer, our ARL Quantix, very interesting for remote locations where there is only scarce electricity on the site, where we don't want to use any gas for the analysis. We do not use a vacuum pump so that we can work with just a small amount of electricity needed for operating the spectrometer. And in that case, we need to work in air atmosphere. And let's see what we can do in air atmosphere with this benchtop spectrometer. So here are calibration curves for nickel and iron. So nickel and iron are not, the X-ray fluorescence of nickel and iron are not absorbed by air, and therefore no trouble. We can align very nicely our calibration points, our calibration samples. On the nickel graph, you see that we have also a very good agreement in terms of alignment of the points with an R square of 0.993. Same thing for iron, also nice alignment of the points with a R square of 9986. So good performance on these two elements. Now, if we move to lighter elements, magnesium and aluminum, so this is much more difficult, should be much more difficult, because magnesium signal, X-ray fluorescent magnesium signal, is absorbed 200 times by air atmosphere. For aluminum, the absorption is 50 times. We would expect that it would be practically impossible to measure magnesium. But in the case of the ARL Quantix, the distance between the sample and the detector and between the X-ray tube and the detector is rather small. We're talking about 3 centimeters. That means the path that the X-rays have to travel through air is short, and we still get a good quantification. You can see here the magnesium curve where we measure magnesium by XRF, but we express on the graph the MgO, the magnesia. Same thing for alumina. We measure aluminum in the sample. We express on the x-axis the alumina concentrations, but we get quite nice calibration curve. We do align all our calibration samples nicely, despite the quite low intensities that we get. So this shows that even in air environment, we have the possibility to use a benchtop EDXRF system in order to do some quantification in a remote location in the middle of the jungle. The drawback would be that sodium then would not be possible in air, because then the absorption is more closer to 2,000 times compared to the 200 times absorption that we experiment for magnesium. Now let's move to other parts of the world and talk about some lithium mines. They are mostly located either in Australia for the spodumene or lithium pegmatites, either in Australia or Canada. These would be prepared as press powders. The other source of lithium is are the brines that are found on salt lakes in the high in the mountains, either in South America or North America. And then it's a measurement that is done on the liquid brines. Advantage of X-ray fluorescence is that there is no dilution needed. The typical elements required are listed here: magnesium, calcium, sulfate, chlorine, sodium, potassium, silicon, mostly for process and production control, but also for checking the final product, the purity or the measurement of the impurities in the final product. Challenges is that lithium cannot be analyzed directly by X-ray fluorescence. So a typical method would be to analyze all the major, minor, and traces in the ores by X-ray fluorescence and get the rest as lithium. That's one way to do that. And the advantage is the easy sample preparation and the fast time to results, thanks to the relatively easy sample preparation. Typical extraction of lithium from salars, so from these salt lakes in the Andes or in North America and South America. You have the extraction of the brines as a first step. There, the lithium will be enriched from 200 ppm to 2000 ppm, evaporation and precipitation to remove sodium, potassium, and also calcium, magnesium. Using calcium and magnesium to remove sodium, potassium. And then transport to the processing plant. Add some calcium oxide and sodium carbonate to remove the magnesium and sulfate. And then we get to a precipitate of lithium carbonate with purity higher than 98.5%. And obviously, during all these steps, it is important to control how well the process works. And this can be done either by atomic absorption or by ICP or by X-ray fluorescence. And X-ray fluorescence will bring some advantages, as we will see. So in the case of X-ray fluorescence, one of the advantages is we can measure directly, for example, the liquids without dilution. Some of the samples may also be pasty. They can also be measured by X-ray fluorescence, placing the sample into a small plastic cup closed with polypropylene 6 micron. And then X-ray fluorescence is able to measure quite a lot of different elements, up to 35 elements, sometimes more if needed. The response is quite fast. The method used are either a fine-tuned calibration, specific calibration for rocks and minerals, or a universal quantitative method called UniQuant, which is a standardless method. And these will be measured with ARL Performix, because the Performix is able to measure liquids thanks to the helium shutter that is included in the spectrometer. Some examples here for lithium brines. So the samples from the various stages of production workflow have been collected, and we have 3 of these samples here in various stages of the workflow. The preparation is pouring the sample into this plastic cup for liquids we can see here on this picture. And here are the typical results, and you can see the sample concentrations, the first one being a high sulfate sample, and then with the sulfate content getting much lower, with a low sulfate content on sample B. But also the purest of the 3 is sample C, with the lower magnesium concentration and the lower calcium concentration in sample C. So these minor contents in the brines will guide plant operation and processes and ensure process and quality control. If we move to the rocks, lithium rocks, then we are going to grind the samples and press the samples, and either an ARL X900 or an ARL Performix can do the job then to measure the various elements present in these lithium pegmatites, and either here or again with fine-tuned calibration or with the unique one standardless method are able to do the job. We have here an example of the calibration. So we start with the soils and sediment calibration that we have fine-tuned and enhanced, we should say, by adding some specific samples, raw material samples, to extend the calibration ranges. We are going to use some raw materials in order to do these calibration range extension. It helps us cover calcium up to 31%, as you can see here in this example, or sulfur to nearly 34%, with a good standard error of estimate over a large range. And this will be used for the typical quality control for the lithium salt extraction process. So finally, something that is quite interesting for the user of X-ray fluorescence is to benefit from turnkey calibrations, which would ensure the spectrometer is fully operational from day one. These turnkey calibrations, they can be either from fused beads sample preparation. For example, we have a general oxide calibration that includes 12 oxides in various minerals and products, like slags, cement, limestone, marl, sand, laterite, iron ores. All these materials can be covered with one single calibration. Then we have a ceramine calibration where we have doubled the number of oxides that are covered, so 24 oxides, again in various rocks and minerals and ceramics. We have the ISO 9516 for iron ores that I've described previously. And then we've also press pellet sample preparation and calibrations on press pellets, either for soils and sediments with 7 major oxides and 28 trace elements, calibration for rocks and minerals, 9 majors, 26 trace elements, and then different calibrations for various minerals, limestone and dolomites, alumina, feldspar, where we can do a differentiation between the calcium fluoride and the calcium carbonate in the sample, and also others on special request. So that's my final slide, and I'm going now to hand over to Linkschneider for the conclusion. Thank you very much for your attention.
Thank you, Didier. As we conclude our presentation, let's recap the key features that make the ARL X900 a great choice for accelerating your materials analysis. The instrument offers configuration options for both simultaneous and sequential WD-XRF, providing analytical flexibility and speed. By integrating the XRF and XRD into a single instrument, we offer a unique solution for the mining applications. Our turnkey solutions are tailored especially for mining industries. The full automation allows for unattended analysis. The ARL Performix spectrometer offers fast analysis on lithium brines, and the ARL Quantex Air version offers analysis for remote sites without any need for gas or pumping. I'm really convinced that the ARL X900's exceptional reliability and analytical performance, together with our full XRF portfolio, will bring significant value to your operations, allowing you to focus on enhancing product quality and operational efficiency in your lab and beyond. Thank you very much for your attention.